everyone, my name is Madhuri Gupta, Assistant Professor, Department of Computer Science, Chhattisgarh Swami Vivekanand Technical University, Bhilai. Today our topic is learning and planning. So, we have the agenda of the class, what is learning, different types of learning, planning, goal stack planning, block word problems and examples. So, what is learning? Learning in AI refers to the process by which a machine or computer systems require knowledge or the ability to perform tasks through experience, data and experimentations. Rather than being explicitly programmed, learning is a fundamental aspect of AI that enables machine to improve their performance on a wide range of tasks and adapt to new situations. There are three main types of learning in AI. First, supervised learning. In supervised learning, a machine learns from a labeled data set where each input is associated with the correct output. The algorithm learns to map input data to output data by identifying patterns and relationships in the parsing data. This type of learning is often used in tasks such as image classification, speech recognition and natural language processing. Unsupervised learning. Unsupervised learning involves learning patterns and structures in data without explicit labels. The algorithm tries to identify hidden patterns or group similar data points together. Clustering and dimensionality reduction are common tasks in unsupervised learning. Examples include clustering customer segments based on purchase history or reducing the dimensionality of a data set for visualization. Next is reinforcement learning. Reinforcement learning is a type of learning where an agent learns to make decisions by interacting with an environment. The agent receives feedback in the form of rewards or penalties based on its actions. The goal is to learn a policy that maximizes the cumulative reward over time. Reinforcement learning is used in applications such as game playing, robotics and autonomous systems. In addition to these main types of learning, there are other approaches and variations such as semi-supervised learning, self-supervised learning and transfer learning, which leverages different types of data and learning paradigms to improve AI performance. Learning in AI often involves the use of neural network, which are computational model inspired by the structure and functions of the human brain. Deep learning, a subset of machines learning, focuses on training deep neural networks with many layers to handle complex tasks such as image recognition and natural language understanding. Overall, learning is a critical component of AI that enables machines to generalize from data, adapt to new information and improve their performance over time, making AI system more capable and versatile. Planning in artificial intelligence refers to the process of generating a sequence of actions or steps to achieve a specific goals or solve a particular problem in a given environment. It is a fundamental aspect of AI that involves reasoning, decision making and creating a strategy to reach desired outcomes. Planning is commonly used in robotics, autonomous systems, game playing and various other AI applications. Here are some key components and components of planning in AI. First, state representation. In planning, the environment is typically represented as a set of states, where each state describes the current situation or configuration. The initial state represent the starting point and the goal state represent the desired outcomes. Next, action representation. Planning involves defining a set of actions or operators that can be applied to change the current state. Each action has preconditions, that means condition that must be true before the action can be executed, and affects changes to the state after the action is executed. Next is goal specification. The goal of the planning is to find a sequence of actions that transform the initial state into a state that satisfies a specified goal condition. The goal condition is typically expressed in terms of desired properties or state variables. Next is search algorithms. Planning often involves searching through a space of possible actions, sequences or plans to find a solution that achieve the goal. Search algorithms such as depth first search, breadth first search, A-star search and heuristic based search are commonly used to explore the state action space efficiently. Next, heuristic. Heuristic are rules or functions that estimate how close a state is to the goal. They are used to guide the search process by selecting promising actions and paths. Heuristic based search algorithm like A-star search use this heuristic to prioritize explorations. Optimality. Depending on the problem, planning may aim to find an optimal plan that achieves the goal with the fewest actions, lowest cost or shortest time. Other times, satisfying solutions without guaranteed optimality may be acceptable. Next is partial overavailability. In some planning problem, the agent may have incomplete or uncertain information about the environment. This is known as partial observability. And planning in such a situation is often referred to as partial observable planning. Next is plan execution and monitoring. Once a plan is generated, it needs to be executed in the real world. Monitoring and adaptation may be necessary if the environment changes or the plan encounters unexpected obstacles. Next is hierarchical planning. In complex scenarios, planning may involve hierarchical decomposition where high level plans are broken down into sub-plans for different components or agents. The hierarchical approaches can simplify the planning process for large scale problems. Next is learning and adaptation. Some planning systems incorporate machine learning techniques to improve their performance by learning from past experience or adapting to changing environments. Planning in AI is a diverse field with various formalism and algorithm, and it plays a crucial role in enabling autonomous agents and systems to make intelligent decisions and achieve their objectives in dynamic and uncertain environment. Now, understand the goal stack planning. Goal stack planning is a classical approach to automated planning in artificial intelligence. It is a planning technique that organizes and represents the planning process using a stack-like data structure known as goal stack. This approach was developed as a part of the STRIPS, that means Stanford Research Institute Problem Solver system in the early days of AI. In goal stack planning, the planning problem is framed as a sequence of sub goals that must be achieved in order to reach an ultimate goal. The goal stack is a last in first out, that means LIFO stack, that keeps track of these sub goals. Here is how goal stack planning works. First, initialization. The initial state of the world is placed at the bottom of the goal stack. Next, goal decomposition. The ultimate goal, which is the desired state or outcome, is placed at the top of the goal stack. Next is planning process. The planning system works from the top of the stack downwards, trying to satisfy the current goal on the stack. To achieve a goal, it may require sub goals are pushed onto the stack. Sub goals are typically generated based on the available actions and the current state of the world. Next, action selection. The planner selects actions or operators that can be applied to achieve the current goals or sub goals. These actions are selected based on their preconditions and the current state. Once an action is chosen, it is applied to the state, potentially achieving the goal or generating new sub goals. Next is stack popping. When a goal or sub goal is achieved, it is popped off the goal stack and the planning system continues to work on the next goal on the stack. Next is backtracking. If an action fails to achieve its associated goal or sub goal, the planner may need to backtrack by ongoing the last action and trying alternative actions or approach. Goal stack planning continues this process of working through the stack of goals, selecting actions, achieving sub goals and backtracking as needed until the ultimate goal is reached or determined to be unreachable. Now, we have advantages of goal stack planning. It provides a structured and intuitive way to represent and solve planning problems. The LIFO stack structure naturally handles goal decomposition and sub goal generations. It can handle complex planning problems with hierarchical goals and sub goals. Disadvantages of goal stack planning. It may not be as efficient as some modern planning algorithm for large scale problems. It may not handle uncertainty or incomplete information well. While goal stack planning is a classical approach, modern AI planning systems often use more sophisticated and efficient techniques such as heuristic search and domain specific optimization. However, goal stack planning remains a valuable concept in the history of AI planning and provides a foundation for understanding the principle of goal driven problem solving. Let us walk through a simple example of goal stack planning to illustrate how it works. In this example, we will consider a scenario where a robots need to make a sandwich. The robots has a set of action it can perform to achieve this goal. So, we have initial state, the robots is in the kitchen. The kitchen has ingredients like bread, lettuce, tomato and cheese. The robot has no sandwich. Goal. The goal is to make a sandwich consisting of bread, lettuce, tomato and cheese. Now, let us use goal stack planning to achieve this goal. First, initialize goal stack. Goal stack, make a sandwich. Next, work on top goal, that means make a sandwich. The robot realizes it needs bread, lettuce, tomato and cheese to make sandwich. It pushes sub goals onto the stack. Goal stack, make a sandwich, get bread, get lettuce, get tomato, get cheese. Work on sub goals, get bread. The robot select an action, go to the pantry if the bread is there. After reaching the pantry, it select another action, take bread. Goal stack, make a sandwich, get lettuce, get tomato, get cheese. Work on sub goals, get lettuce. The robot select action to go to the fridge and take lettuce. Next, goal stack, make a sandwich, get tomato, get cheese. Next, work on sub goals, get tomato. The robot select an actions to go to the fridge and take a tomato. Goal stack, make a sandwich, get cheese. Work on sub goals, get cheese. The robot selects action to go to the fridge and take cheese. Goal stack, make a sandwich. Work on top goal, that means make sandwich. The robot now has all the ingredients, so it pushes the sub goals, assemble sandwich onto the stack. Goal stack, make a sandwich, assemble sandwich. Work on sub goal, assemble sandwich. The robot select actions to take 2 slices of bread and place lettuce, tomato and cheese between them. Goal stack, make a sandwich. Work on top goal, make sandwich. The robot has successfully assembled the sandwich, so it pops the top goal of the stack. Goal stack. Next, goal stack empty. The robot has achieved the ultimate goal of making a sandwich. In this example, the robot uses the goal stack planning to break down the complex task of making a sandwich into a sequence of sub goals. It selects action to achieve each sub goals and uses a stack to keep track of the goals. Once all sub goals are satisfied, the robot successfully makes the sandwich. Goal stack approach or planning provides a structured approach to solving such problem by decomposing them into manageable steps. Let's have another example of block word problem to illustrate goal stack planning. In the block word, there are a set of blocks and the goal is to arrange them in a specified configuration. So, we have initial state 3 blocks A, B and C. Block A is on the table, block B is on the table, block C is on the top of the block B. The goal is to have block A on top of block B. Now, let us apply goal stack planning to achieve this goal. First, initialize goal stack. Goal stack A on B. Work on top goal A on B. The robot realizes that it needs to achieve the goal A on B. It pushes sub goals onto the stack. Goal stack A on B. Clear A, clear B. Work on sub goal, clear A. The robot checks if block A is clear, that is not on top of any other block. Since A is initially clear, it does not need to do anything specific for this sub goal. Goal stack A on B, clear B. Next, work on sub goal, clear B. The robot checks if block B is clear. However, it finds the block C isn't on the top of B, so it needs to do it need to clear C first. It pushes a new sub goals onto the stack. Goal stack A on B, clear B, A on C. Work on sub goal A on C. The robot realizes it needs to move block A on top of C, clear B. It pushes more sub goals. Goal stack A on B, clear B, A on C, clear A, move A to C. Work on sub goals, clear A. The robot determines that block A is not clear, it's on B. It pushes a sub goal to clear A. Next, work on sub goals, clear A. The robot successfully moves block A to a clear spot, clearing A. Goal stack A on B, clear B, A on C. Work on sub goals A on C. The robot proceeds to move block A on top of C, achieving these sub goals. Goal stack A on B, clear B. Work on sub goal, clear B. Now the robots can clear block B as block A is on top of C and C is clear. Goal stack A on B. Work on top goal A on B. Finally, the robots moves block A on top of B, completing the goal stack. Goal stack is empty. The robot has successfully achieved the ultimate goal of having block A on top of block B. In this example, the goal stack planning method is used to break down the problem of arranging blocks into a sequence of sub goals, which are then achieved through a series of actions. Each sub goal is added to the stack and worked on until the ultimate goal is satisfied. Demonstrating how goal stack planning helps in solving complex problems step by step. Goal stack planning for block word problems. So, we have the example, we have initial state where we have A on B, then C and D, and our goal is to arrange A on B and C on D. In this medium article, we will take look at the block word problems and implement goal stack planning to solve the same. What is block word problem? This is how the problem goes. There is a table on which some blocks are placed. Some blocks may or may not be stacked on other blocks. We have a robot arm to pick up or put down the blocks. The robot arm can move only one block at a time, and no other block should be stacked on top of the block which is to be moved by robot arms. Our aim is to change the configuration of the blocks from the initial state to the goal state, both of which have been specified in the diagram above. So, what is goal stack planning? Goal stack planning is one of the earliest method in artificial intelligence in which we work backwards from the goal state to the initial state. We start at the goal state and we try to fulfill the preconditions required to achieve the initial state. These preconditions in turn have their own set of preconditions which are required to be satisfied first. We keep solving these goals and sub goals until we finally arrive the initial state. We make use of a stack to hold these goals that need to be fulfilled as well as the actions that we need to perform for the same. Apart from the initial state and the goal state, we maintain a world state configuration as well. Goal stack uses the world state to work its way from goal state to initial state. World state on the other hand start off as the initial state and ends up being transformed into the goal state. At the end of this algorithm, we are left with the empty stack and a set of actions which help us navigate from the initial state to the world state. Representing the configuration as a list of predicates. Predicates can be thought of as a statement which helps us convey the information from a configuration in block word. Given below are the list of predicates as well as their intent meaning. On AB, that means block A is on B. On table A is on table. Clear A, nothing is on top of A. Holding A, arm is holding A. Arm empty, arm is holding nothing. Using these predicates, we represent the initial state and the goal state in our example like this. Initial state on BA and on table A and on table C and on table D and clear B and clear C and clear D and arm empty. So, in this diagram you can see the A on B and then C and D. Goal state on CA and on BD, on table A and on table D and clear B and clear C and arm empty. So, you can see the goal state A on C and D on B. Thus, a configuration can be thought of as a list of predicates describing the current scenario. Operations performed by the robot arm. The robot arm can perform 4 operations. Stack XY, that means stacking block X on block Y. Unstack XY, that means picking up block X which is on top of block Y. Pick up X, picking up block X which is on top of the table. Put down X means put block X on the table. All the 4 operations have certain preconditions which need to be satisfied to perform the same. These preconditions are represented in the form of predicates. The effort of these operations is represented 2 lists AND and delete. Delete list contains the predicates which will erase to be true once the operation is performed. Add list on the other hand contains the predicates which will become true once the operation is performed. The preconditions add and delete list for each operation is rather intuitive and have been listed below. So, you can see in this table the initial table which represent all the activities. Next, for example, to perform the stack XY operation, that means to stack block X on top of block Y, no other block should be on top of Y, that means clear Y, and the robot arm should be holding the block X, holding X. Once the operation is performed, these predicates will erase to be true. These predicates will cease to be true. Thus, they are included in delete list as well. Note, it is not necessary for preconditions and delete list to be the exact same. On the other hand, once the operation is performed, the robot arm will be free, that means arm empty, and the block X will be on top of X, top of Y on X comma Y. The other 3 operators follow similar logic, and this part is the cornerstone of goal state planning. As you can see, we have stored the steps from initial state to the goal state in the variable steps. In this example, steps is equal to pick up C, put down C, unstack BA, put down B, pick up C, stack CA, pick up B, stack BD. The visual representation of our steps variable looks like this in the diagram. Thank you for watching, and we will see you in the next lecture.